We are now recording. We'll go from current slide. And, no, we shouldn't. Sorry. Yeah, I did. That's right. Okay. Good to go. Thank you. Now, there's a number of announcements to be made first, so let's get started on those. I'll try to hopefully manage to get them all in without forgetting something. Okay, number one, everybody know about the student course evaluations? Yay? Okay. Working on them? I've already done them? Okay, good deal. Don't forget to do them. Please do them before August 8th. Way before August 8th. I'm not going to be here to remind you on August 8th, so get them done. Okay. Now, let's talk about how the term's going to end. Okay? Today's Wednesday. Next is the last day of class. Getting sad, isn't it? Okay? So, let me just tell you, my office hours today remaining are 5:30 to 6 this afternoon. Okay? Now, let me talk about office hours from now on because they've been really screwy lately because I've had to go to the Birmingham campus for one thing or another just about every Tuesday and Thursday for several weeks now. But I think all that's pretty much over with except one thing, and I'll talk about that in a minute. So, tomorrow, office hours on this campus, 8 to 8:30. I've got a class in here, 8:30 to 10:45. Then office hours, finally back like we were at the beginning of the term, 10:45 until, now this is close to what we were. I'm now saying 4:15. Before I was saying 4:30 because I had to go to the Birmingham campus. Found if I left at 4:30, I couldn't get the class set up in time, so I'm leaving at 4:15 now. Going to try to anyway. So tomorrow and Tuesday will be 8 to 8:30, 10:45 to 4:15. Okay? Then I'll be over there after that. Monday was just like today, 8 to 8:30 in the morning and 5:30 to 6 in the evening. Oh, yeah, that's Monday. Now, after Monday and Tuesday of next week, those are the last 2 days of classes. Yours will be Monday, Tuesday, Thursday classes on Tuesday. After that, Wednesday and Thursday are final exam days. Okay, so let me back up for a moment here. I've got run off, that's what I was running off between the classes, your last test. Now, I'm making a guess on how far we're going to get. If we don't get that far, I'll let you know Monday, only go through thus and so. If we get further along, you just get bonus. Okay, I mean, you're in good shape. Okay, so anyway, I'll give you the test today so you can start working on them this weekend. So you don't have them all to do next week. Okay. Now, technically, your final is due on Wednesday. Okay. Here's a little bit of a problem with Wednesday. Now, okay, after Monday, that's the last class, we don't have any other formal classes. Okay. So let's talk about Wednesday then, first day of finals. I'll be here on this campus from 8 in the morning, unfortunately only till about 12:30 in the afternoon. Why? They've called a meeting on the Birmingham West campus for 1 o'clock. So I will be on the Birmingham West campus. I'll leave here about 12:30, try to get there by 1 o'clock, and then once I'm over there, I think the meeting will probably go about 2 hours. I'm hoping no longer than that. I'm hoping less than that. But rather than wasting another 30 minutes driving back here, I will just work over there. So probably 3 to 6 I'll be over there. So if you want to get your final to me Wednesday, you can either get it here between 8 and 12:30. That would be fine. I'll be on this campus. If you want to get it to me on the other campus, I'll be there. I won't be in the office there, but I'll be in the office there probably 3 to 6, maybe a little before 3, hopefully. But you can always take it by the office. If Miss Saxton is there, she's my boss's secretary, you can give her the test, and I'll get it when I come back from the meeting. Okay. Or, if you don't want to make a special trip to the Birmingham campus, unless that's more convenient for you, if you turn it in after 12:30, you can slide it under my door. My office door is 265. I'll point out again where that is. You go out of the door here, take a left, go down this half flight of stairs right there, go almost all the way to the end of the hall. The last office on the left is 265. Okay? So, if you bring it in, and I've already left for the Birmingham campus, you want to just slide it under my door, that's fine. Okay? Or you can bring it in any time Thursday. Or let me give you the times on Thursday. I'll be here on this campus from 8 in the morning until about 4 o'clock in the afternoon. I'm going to have to leave to go to the Birmingham campus again, so I'm going to leave 4 to 4:15 again. If you don't get it to me, let's say by 4 o'clock Thursday afternoon, I'm probably not going to see it because I'm going over there. We'll be there the rest of the day. Class gets over with at 6:30. I'm not coming back here, and I'm going to put in to have Monday off, so I won't see it again until I get back for fall term. So that means if you don't have it in to me before 4 o'clock on Thursday afternoon, you're getting it incomplete. And then when I get back from for fall term, I'll get it graded. If it's under my door then, I'll get it graded, change the incomplete to whatever grade you earn. Okay? So please, if possible, get it to me before 12:30 on Wednesday, or slide it under my door after 12:30 on Wednesday, or before 4 o'clock on Thursday. And that way, I'm sure to get it, hopefully sure to get it graded and done. So any questions about how we wrap things up there? Okay? Well, I'm planning not to be here the following Monday. And that's our last day. I'm planning to take that day off. Any questions? All right. Please do the student course evaluations. We'll go over a lot of that stuff again on Monday, just in case anyone missed it or forgets it. Okay. And here we go. More tests coming in. Now, and by the way, before today, everything that's been turned in has been graded. I don't have it on Blackboard yet. Hopefully, now that all those other things on the other campus are taken care of pretty much, I'll be able to start getting things on Blackboard. So I'm looking forward to that, probably starting tomorrow. May not get that far tomorrow, but at least I'll get started. Okay. Any questions? Okay. We're in Chapter 11. This is Vectors in the Geometry of Space. 11.2, Space Coordinates and Vectors in Space. So we've moved from plane coordinates, two-dimensional space, 2 dimensions, to 3-dimensional space, which is space, okay? 3 coordinates. We had talked about, we had done example 1 on page 763, and we were down almost to example 2. Ran out of time right about here, and I think we did the first part. A sphere with a center x0, y0, z0, and a radius r is defined to be the set of all points x, y, z, such that the distance between x, y, z and x0, y0, 0, the center, is that radius r. So if that's the center, all the points in space around that are r distance from there. So you can use the distance formula, we just did, to find the standard equation of the sphere, radius r, centered at x0, y0, z0. And we did that last time and found this, okay? X minus x0 squared plus y minus y0 squared plus z minus z0 squared is equal to r squared. That's one way of expressing this. Here's the keys. Your coefficients of your variables, x, y, and z, are all the same. Okay? In this case, 1. Okay? They're actually x squared, y squared, and z squared. Secondly, plus signs between all 3 of them. That's positive. Okay? R squared is at the end. Okay? The x0, y0, z0 just moves it from the origin to wherever that center may be. And then the r as you can space there. Okay. Now, this we didn't get to last time. The midpoint of the line segment joining the points x1, y1, z1, and x2, y2, z2 has these coordinates. Midpoint, midway between, basically, midway between x1 and x2 is x1 plus x2 over 2, y1 plus y2 over 2, z1 plus z2 over 2. The average between each of those coordinates, x1, x2, x2, y1, y2, z1, and z2. The midpoint is the average value in between each of those. So there's your midpoint formula. We don't use that in quite as much as we do distance formula, but there will be occasions that you'll use midpoint. Perhaps like coming up in example 2. And they don't show example 2, I don't think. No. Okay? So let's see if we can find example 2. Okay? And Marjorie decided she would show up today. Okay, good deal. All right. Now, since there probably, hopefully, will be more people coming in too, before anyone leaves today, remind me, I'll go through, try to do it quickly, the announcements I just did for the rest of you, so you'll get to hear them too. So hopefully there'll be more coming in that just won't be you, but otherwise I can just tell you after class. All right, so here's example 2. Whoops. Get my pen set up. Okay. Find the standard equation of the sphere that has points 5, -2, 3, and 0, 4, -3 as endpoints of a diameter. Okay, we want the equation, standard equation of a sphere. I can't write very well, but there we go. That's what we're looking for. These are the endpoints of the diameter. So, what does these tell you? Yeah, that's it. But number one, yeah, you're moving in the right direction.
I would say I had a formula was 5, literally 5 plus 0 over 2.
All right. What you're finding is this is the diameter of the sphere.
Okay.
Diameter goes from one end to the other. The midpoint of that is going to be the center of the sphere. Exactly. If we know the center of the sphere, we can get it in the standard formula by what you were saying. Okay? So, let's get the center of the sphere. And you were just telling me what that was. What would that be? 5 minus 0 over, plus 0 over 2. Okay, -2 plus 4 is?
Oh, never mind. It's
2 divided by 2 is? Okay, and the last one? Say again? I can't hear. 0. Excellent, excellent, excellent. There's the center of that sphere. Now that we have the center of the sphere, oh, we need something else, don't we? Marjorie was going to tell us how to do it with the radius and stuff like this, but guess what? We don't know the radius. Or do, oh, distance formula, and how does that go? The square root of? Say again?
Change in x squared. The change in x squared.
Okay, which change of x?
X minus x.
The center and the
The center to the other. So we need to go from this one to one of those two. So pick which one you want to go to and tell me how to do it.
We'll go to 0, 4, negative 3.
I'm sorry?
We'll go from the center to 0, 4, negative 3.
Okay. Tell me how.
It would be 5 halves squared
To 0. Okay. Okay.
plus. Are you subtracting the 2?
Yeah.
Yeah, okay. So it will be negative 3
Negative 3 squared
plus 3 squared. It's going to be 25 fourths. Okay. Plus 9 plus 9.
Okay. Now 25 fourths would be 6 1/4, right? So this would be 24 1/4, which would be 97 fourths. I think so. Is that right? I'm doing it in my head, and my head is sort of foggy. Not right. Huh? Is that right? Okay. Which would be the square root of 97 over 2. I think. Look at that. I think it's all right. Okay. Now, do we really need R? Or would we rather have, what's the formula? Tell me the formula for the standard equation of a sphere.
Square root.
It's going to be squared, right? R squared is what we're really interested in. So we'll don't need that anyway, just that one. 97 fourths. Okay. So, what would it be then? Standard equation of a sphere. I'll start off with the open parentheses. X minus help me somebody. 5 halves squared plus, always plus for the sphere, right? Y minus 1 squared plus second,
Z minus 0. Or
yeah, z squared equal 97 fourths. Okay. Now that's as good as any. In fact, that's how they leave it. X minus 5 halves squared plus y minus 1 half squared plus z squared is equal to 97 fourths. Okay. I would be real tempted to divide everything by 97 fourths and make this a 4 times this over 97 plus 4 times this over 97 plus 4 times this over 97 equal 1. That to me is a little more standard, but the book's not doing that, so it's perfectly fine to have it like that. Any questions on that? All right. All right, here he is. Had me worried the world was coming to an end or something. You are here. Okay. All right. Now, we've just done example 2 on page 763. That's in chapter 11, Vectors in Geometry of Space, 11.2, Space Coordinates and Vectors in Space. Which leads to vectors in space. Okay. So this is kind of the second part of this verse, of the second section here in 11.2. In space, vectors are denoted by ordered triplets, not ordered pairs. Two space planes, ordered pairs are fine. In space, you need an ordered triplet. Now, again, I think I mentioned this before. Both words are important. Ordered, the order matters, and triplets got to be three of them. So here's a typical vector V. Bold here is V. If I was writing this, it would be an arrow over it. Its triplet, its coordinates would be V1, V2, and V3. This would be in the X direction, the Y direction, and Z direction. Again, though, the zero vector, you have to have it to be a vector space, and the zero vector would then be an ordered triplet, as opposed to an ordered pair, 0, 0, 0. Okay? Problem with the zero vector, it has neither magnitude nor direction, but it's still considered a vector. And using the three unit vectors, I being 1, 0, 0, J being 0, 1, 0, and K now being 0, 0, 0, because these are unit vectors, I don't write bold, but I would be putting a caret on top. That indicates to me it's a unit vector. And these are your standard unit vectors, so you could write this original vector V here, which is bold. Now they have a Times New Roman as opposed to Arial or something like this. Why, I don't know. But this would be V1I plus V2J plus V3K. As I said before, these are the coordinates in each of those directions. Okay, so here would be your typical vector. V1I, it looks like V1 is a little bit more than 1. I'm going to just guess maybe 1.5, 1.5, something like that. V2J, maybe just a tad longer than 1, so maybe 1.3 or something like that. And your K component up here, this looks like maybe 3K or something about like that. So V1, V2, V3, the components in the X direction, components in the Y direction, component in the K direction. Okay? X, Y, G, I, J, K, I get them all crossed up. You know, mix them up, mix and match. Okay. If V is represented by the directed line segment from P, some old point P here, initial point, to some terminal point Q, where P is P1, P2, P3. Those are coordinates of the point to Q, which is Q1, Q2, Q3. Coordinates of that point is shown here. Then the component form of V, written just like we did before, V being this vector that goes between those two from P to Q, would be, its V1 would be Q1 minus P1, V2 would be Q2 minus P2, and V3 would be Q3 minus P3, and that's the vector. Okay? So, any questions on that? Now, in this one, you can't tell looking here, but you can when they put it down here. Your X1, your V1 looks like it's slightly positive. V2 looks like it's somewhat positive. And looking at this, V3 also appears to be positive. These two can tell you about X and Y. This tells you about the Z up here. So that looks like that's a vector. But you see, looking at this, you don't know if it's going that way, this way, or which way. But looking at these, you know it's coming out of the board and going up. Okay. Hard to represent a three-dimensional figure on a two-dimensional board. They do a good job. I don't. All right. Some of the characteristics of vectors in space. If U is a vector, U1, V1, U1, U2, U3, vector V is V1, V2, V3, are in space, 3 dimensions in space. C is any old scalar, any real number scalar, C. Usually we don't take it 0, but it could be. Could be positive or negative, rational or irrational, whatever. The equality of two vectors, U is equal to V if and only if U1 is V1, U2 is exactly V2, and U3 is precisely V3. That's the only way those two will be the same. Okay? In component form, if V is represented by the directed line segment from P, now these are coordinates of a point, these are components of a vector when you have the angle brackets. P is P1, P2, P3, Q is Q1, Q2, Q3, coordinates of the 2 points. Then the vector V in component form, V1, V2, V3, would be always final minus initial, okay, terminal minus initial. Q1 minus P1, comma, Q2 minus P2, comma, Q3 minus P3. The length of the magnitude of a vector, very much just a direct extension of what we did in 2 dimensions. The magnitude of V, and that double bars means magnitude, the square root of V1 squared plus V2 squared plus V3 squared. The unit vector in the direction of V, just like we did before, is the vector V divided by its magnitude. That gives it a magnitude, the unit vector magnitude of 1. You could write that as 1 over the magnitude of V times vector V, which is V1, V2, V3. That's close to the form we usually do it. Now, of course, there is no unit vector in the direction of a 0 vector because a 0 vector has no direction and it has no magnitude, so it can't have a unit vector, so the vector V can't be the 0 vector. Vector addition, doesn't matter what order either, but V1 plus U, V plus U, everything do by components. V1 plus U1, comma V2 plus U2, comma V3 plus U3. That's it. Okay? Scalar multiplication, is that scalar C multiplied by vector V. It'd just be C times V1, comma C times V2, comma C times V3. In other words, you distribute the C across all 3 components. Okay? Make sense? Just a direct extension of what we were doing before. Okay? Here's example 3. By the way, example 3, it's also located at larsoncalculus.com for an interactive version of this type of an example. So it says find the component form and the magnitude of vector V having initial point, so parentheses here, -2, 3, 1, terminal point 0, -4, 4. Then find the unit vector in the same direction of V. Okay, so let's do the first. Component form of the vector V. I can't write bold, so I'll put an arrow over the top. What would be its component form? Anybody? Second? -2. How'd you get -2? Second?
Final minus initial.
Okay, and what is your final? Which is? 2. Okay, got it. All right. Next. -7. Next. 3. Excellent. Okay. Now that you've got it in component form, pretty easy to find its magnitude. What would be the magnitude of that vector V? The square root of 4 plus 49 plus 9. Easy to write. What does it add to? That's 58, and 4 is 62. Square root of 62. I don't think there's a perfect square lurking in there, is there? 4 won't go into that. I don't think anything will, so we'll leave it as root 62. Yeah, that's what they got to. All right. So now that we found both the vector and its magnitude, it's pretty easy to come up with a unit vector in the direction of V. So it's all right if I call that U, but put a hat over it in the direction of V. Okay, that's not a standard notation, but it'll work for me. What would that be? Going to be a vector. Second? Okay, are you saying 2 over square root of 62, comma, negative 7 over square root of 60, if I could write, 62, comma, 3 over the square root of 62. Okay? Now, we claim that's a unit vector in the same direction of v. If we got v right, you know that has to be the same direction because it's just multiplied by a scalar. So the direction doesn't change. It happens to be a positive scalar at that. Now the question is it a unit vector? Does it have a magnitude of 1? And hopefully you'll see that has to be, because if you square this, you get 4, 49, 9, same thing you got here. So its magnitude would be root 62, and root 62 divided by root 62 is 1. So yes, that's your unit vector in that same direction. 2 over root 62, negative 7 over root 62, 3 over root 62. All right. That's how we did it. Let's see how they do it. Can I leave this, or, erase it, or do you need it left a little bit longer? Okay. All right. The components form of V would then be terminal minus initial, Q1 minus Q2, Q1 minus P1, and Q2 minus P2, Q3 minus P3, which would be 0 minus a minus 2, negative 4 minus a minus 3, minus a 3, and 4 minus 1. Okay? So that gives us our 2, negative 7, 3. Just like you found. Okay? Magnitude of that, just take the square root of the sum of the squares. Square root of 2 squared plus negative 7 squared plus 3 squared. Who cares about the signs there when you're squaring them? They all go positive. So 4 plus 49 plus 9, that's root 62. Then the unit vector in that direction, and they use u as well. Now, not always when they write a u is it a unit vector. That's why I like to put a cap over it to remind me it is. But then this would be the vector v divided by its magnitude, which would then simply be 1 over root 62 times vector v, which would be 2, negative 7, 3. Let's see if they do one more step. Yeah. Then they move it, this scalar inside, and it would be the vector 2 over root 62, negative 7 over root 62, and 3 over root 62. Any questions? All right. Now, recall from the definition of scalar multiplication that positive scalar multiples of the non-zero vector v have the same direction of v, whereas negative multiples have exactly the opposite direction of vector v. In general, two non-zero vectors, u and v, are parallel to each other when there is some scalar c, positive or negative, such that u is that scalar times v. Okay? So here's your definition of parallel vectors. Two non-zero vectors, u and v, are parallel, either this way or that way, when there's some scalar c such that u is equal to cv. Okay? Pretty direct definition. So here's an example in this figure. The vectors u, v, and w are parallel because u here appears to be exactly, let's see if it is, close to it, exactly 2 times v, same direction, but twice the magnitude, but w is same magnitude, but opposite direction, so that would just be minus v. So both of those are multiples of the same vector, different multiples, so they all three got to be parallel. Okay? Make sense? Pretty straightforward. Here's example 4. Yep. Vector W has initial point 2, negative 1, 3, terminal point negative 4, 7, 5. which of the following vectors is parallel to that W? Well, what are we going to have to do to find that out? What would you suggest? Anybody? Second. Okay, find the component form of W. It's a vector W, and its component form would be?
2.
I'm sorry?
2.
Did you say 6?
Oh, sorry. 2 that's negative. Yeah.
Okay. Close, but not quite. Did you just say 6? Negative 6, okay? Final minus initial, right? Terminal minus initial. Be negative 6, comma, 8, comma, 8, comma, 8, close. No, that's not right. You're leading me astray. Okay. Okay, what would it be? 2. Okay. Now, so which of these two would be parallel to W? Well, so far, this is a multiple of that, and the multiple would be negative 2. That's a multiple of that, and the multiple would be negative 2. That one looks like it would be a multiple of negative 2. So certainly U is parallel to W. How about this one? That's a multiple of negative 2 this way, multiple of negative 2 that way. But this is a multiple of 2 this way, so no, that one's not. Okay? U would be, V is not. Now here's my shorthand for this. I think it's pretty standard. U is parallel to W, or W is parallel to U. It doesn't matter. It is not parallel. W is not parallel to V. You don't have to write it that way, but to me that's a little bit of a shorthand. Okay. U is parallel to W, yep, and not parallel. V is not parallel to W. Okay. Let's erase. Oh, let's see. Maybe they can get by. Yeah. Begin by writing W in component form, with exactly what we tried to do. Okay. And they wrote the component forms that way. Final or terminal minus initial. Okay. Negative 6, 8, 2. Okay. Just like you got. And because U is exactly 1/2 of W, that is a multiple, you conclude that U is parallel to W. But in the second case, we want to find if there's a C that is C times W will equal V, I believe it was. I think that was the order. Well, let's see if that works. You get a minus 2 as a multiple for the first two, but a positive 2 for the next one. Nope. Not parallel, for sure. Okay. Means that the vector 12, negative 16, 4 is not parallel to negative 6, 8, 2. Now, you want a little cheap way to do it? I mean, at least to approach it. For these two to be parallel, either the signs are exactly opposite, as they are here, here, but not there, can't be part, right? Or they're exactly the same, okay? But they can't be to the opposite and to the same or something. That's irrespective of whether they're multiples of each other. If the signs aren't agreeable, this is plus minus plus, so this one would have to be plus minus plus or minus plus minus. Can't be anything else. This is minus plus plus. So just based on that alone, you could have said, no, they're not parallel. Okay? Without even messing around to see what the C is, just look at the signs. Now, just because the signs are the same, then you have to check and see if the multiples are the same as well. All right. Any questions on that? All right. They are not going to do example 5, 6, or 7. Okay. So let's us do it. Okay. Example 5. Determine whether these points P, which is 1, negative 2, 3, Q, which is 2, 1, 0, and R, which is 4, 7, negative 6. Now remember, these are points. These are not vectors. These are coordinates of 3 points. We want to determine whether they are collinear or not. Now, what does it mean to be collinear? Collinear. It's got to be at least two conditions met. Same what?
They're on the same line.
They're on the same line. That covers it. So what 2 things can we measure to determine if they're on the same line? Okay, yes. We certainly start there. If they don't have the same slope, they can't be on the same line, right? So they've got to have the same slope. So how do we determine the slope? Say again?
I know it's y2 minus y1
Okay, let's do it for any 2 pairs of them. Okay? So let's just call it, how about PQ? What would that vector be? Say it a little louder. Yeah. Okay, and what would it give you? A little louder.
3.
Really?
1 plus 2.
Okay.
Or is it 2 minus 1?
I thought it was difference. Say again? 1, comma, 3, comma, negative 3, is that what you said? Yeah, okay. There would be the vector between P and Q. Now, if you had chosen QP, which would be perfectly fine, the signs would just be changed, okay? Now, what's the next one you want to consider? Which one? RP, okay, we'll do it that way. Doesn't really matter, okay. It'll be a vector. Say again. Negative 3, you said? This is a negative 2. Is that the one you're talking about? R. It's a negative 6. Is that the one you're asking? Okay. I think I wrote it right, yeah, okay. Okay, the first one? Say again?
Or wait, no. Okay, it's 3.
Okay.
Oh.
You said RP. I'm doing what you tell me to, okay?
Oh, okay, I'm sure. Okay, my mind messed up. Yeah,
Negative 3? Is that what you said?
Yes.
I agree with that, okay?
Negative 9.
Negative 9, comma, 9. Okay. Now, the question is, can these be parallel? The signs would indicate so, plus, plus, minus, 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 plus. Yeah, the signs are okay. Are the multiples okay? 3, 3, 3. Yes, they're parallel. Okay? Does that mean they're collinear? Not necessarily. Okay, so how could we then determine if they're collinear? Okay? All right. There's probably several ways to do it. Now, how we kind of messed up, what we did was fine, but how we kind of messed up, we needed really to get the same initial or terminal point, didn't we? And we flipped them. So if we had really done this one as PR, public relations, no, I'm sorry, PR, what that would just be changing the signs, wouldn't it? So let's do that. Okay. That would be a minus, a plus, plus, minus, right? Now, what that did for us is, number one, told us that we still are same slope, right? And they have a point in common, right? P was in common with both of them. So if they're same slope and have the same initial point, they got to be covariant, right? So I believe that would do it for us, okay? And so got it. So wise choice of our initial point on both of them would be fine. Or terminal point, either one, it wouldn't matter. But they had to be one of those the same. All right. Let's move on to example 6. Any questions before I do? All right. You know, back when I was doing my initial announcements, I forgot one pretty important one, okay? And that is this. All your research papers have to be in by Monday, right? And all your tests have to be in by Monday. Research papers, just because that's the deadline. The test, because I'm giving back all your tests on Monday, and if you haven't turned in a test, I can't give it back to you. That means you get a sort of a goose egg for that test, which is not a good idea, okay? So please get me all your research papers and your tests by class on Monday. Now, what does it mean by class on Monday? I'll take them today. I'll even take them tomorrow. Or first thing Monday morning. Slide them under my door, whatever. I need them by Monday, okay? Now, if you wait until Monday to turn it in, can't get it back to you because I don't have time to grade it. But when you come turn in your final, I'll give it back to you then, okay? So I meant to say that one too. Be sure you get everything in by Monday. Now, I did want to look and see. Test 1, according to what I see here, 2 people haven't turned it in. One person who's here and one person who's not here. Test 2, 1, 2, 3, 4, 5, 6 have turned it in. 1, 2, 3, 4, 5, 6 have not. Half of you turned, well, some turned it in today, so that's great. Okay? And knock on wood, I'll try to have them all graded by Monday. We'll see, okay? And I'll try to even have them on Blackboard by Monday. We'll see that too, okay? Finally have some time to grade tomorrow, except that they won't, incompletes from last term due tomorrow, and the planning hearing we did, I'm supposed to have those corrections made by tomorrow. So my day has gotten a lot shorter than what I thought it would be originally. Okay, but that's my problem, not yours. It becomes your problem because I can't turn it in, but at least it's mine. All right, let's do example 6. All right, write the vector v equal 4i minus 5k in component form. That's pretty easy. What would that be?
4.
Second?
4.
4.
-5.
Ooh. What are we missing? We need a 0 in there for our j. Okay? -5. Got it. Got it. Got it. Write the vector in component form. We just did. Find the terminal point of the vector v. This is a completely different v. So this is the AV. Here is the BV. different vector v, 7I, there's plenty of letters in the alphabet, why couldn't they have used a different one, minus j plus 3k. Find the terminal point of that one, given that the initial point P is -2, 3, 5. Okay, this is the initial point. Okay, so what would be your terminal point? And we'll just, you want to call it Q or something else? I don't care. Huh? Q is fine. So what we're looking for is Q. Second? Okay, let me get this out of the way. And you're suggesting a 5 there. Okay, let me write it 5, comma. Did you say 2? Okay. Second? 2 again? Okay. Now how could we check that? If this is supposed to be PQ, then we could subtract this one from this one. That would give us, this minus that is 7. That's good. This minus this is -1. That's good. And this minus this is?
Oh!
Huh?
That's -3, so we'll need to change the 2 to an 8.
It's what?
Change the 2 to an 8.
An 8. Okay. All right. I like that idea. And let me go back and check that one then. And then 8 minus 5, sure enough, is 3. Now, I could hear the wheels grinding away there, you know, as y'all are doing. But remember this, that this is the difference of, is this minus that, right? So therefore, this must be this plus that. So you could just done 5, 2, 8. A little bit easier, but still there. Okay. Does that make sense? Okay. That was the B part. Yeah, 5, 2, 8. I was trying to find it on the page here. And then the C part. Find the magnitude of another vector V. All the letters in the alphabet, and we use the same one 3 different ways, is equal to minus 6I plus 2J minus 3K. Find the magnitude of that, then find the unit vector in the direction of V. So let's first find the magnitude. What would that be? How would we find it? Magnitudes always start with square root. Start with the square root. Okay, -6 squared plus 2 squared, -3 squared, and that would be the square root of 36 plus 4 plus 9, and that would be square root of 49, and that would be 7. Good deal. So there's the magnitude of V. This next part was find the unit vector in the direction of V. So let's just call it unit vector U, and I'll use the subscript in the direction of V. Okay? And what would that be? Help me somebody. -6 over 7, comma, whoa, 2 over 7, comma, -3/7. And what's a real good check that you can make to make sure that's a unit vector? And we've already done it, really. Grab and see if it's equal to 1. Well, that would be if your numerators squared add to the square of this, which of course they do. 36 plus 4 is 40, plus 9 is 49. Yes, it has to be. All right, so there we have oh, okay. I wrote it in component form. They didn't say how to write it. They wrote it as -6/7 I plus 2/7 J minus 3/7 K. Neither one of those is any better than the other, whatever floats your boat. I guess since the original one was given in IJK form, they wanted the answer in that. But both of them are correct. All right, any questions? Okay. If not, can I erase? And we'll do example 7, which is also not listed on the slide set. A television camera weighing 120 pounds is supported by a tripod as shown in this figure. Okay? Represent the force exerted on each leg of the tripod as a vector. Okay? Boo hiss. Okay. I'm going to try my best to sort of get this in place. I don't draw these things well. So let's just do an x-axis here and a y-axis there. Okay, that's how the book did it. Only the y was not nearly in that direction. Let me see if I can get it more like theirs. Maybe something like that. Still probably not quite right, but close. Okay? Now, they draw, or at least they intimate that there's a, at least it looks kind of like a circle, and they say Q1 is at 0, -1, 0. 0, -1, 0. That's Q1. That's a point. Those are coordinates of a point. Q2 appears to be over here about √3/2. This is Q2. 1/2, 0, so the z component is still 0. And Q3, somewhere back here, is -√3/2, 1/2, 0. Okay. And the tripod is somewhere above that. Okay. And here's your camera sitting up here on the tripod, and the weight of the camera is 120 pounds. Now, this is going to be hard to do because one of my lines shows up there, but that's straight down toward the origin of 120 pounds. And that is your I'm going to call it F sub W for weight, 120 pounds. Now, since it's down, I think they're going to call that -2. We'll see. Seems like they should, because it's in the negative z direction. Okay. Now, represent the force exerted on each leg of the tripod as a vector. Okay? So the vectors F1, F2, and F3 represent those forces. So this will be F1, this will be F2, and this will be F3. Those are forces, so let me put arrows over them. Okay. Now, oh, I left something off. This point up here, where the camera is at 0, 0, 4. Now, I think you'll see mine's obviously not drawn to scale too well, but just get over it. Okay. Okay. So, vector 1 here, F1, okay, would be, this is point P, I didn't write my P there, P to Q1, so F1 would be the vector P to Q1, and that would be what? This basically is going to answer your question right here. What would that be? Anybody? Okay, 0, I'll buy that one. -1. -4. Okay. Now, oh man. All right. That's at least the direction of F1. My eyes are going crazy on me here. All right, that's the direction. It probably is going to have a scalar multiple by it because it's got to be basically a third of the weight of that. Let's assume that is a circle down there and equal weight on all three. So it needs a scalar multiple of it such that it's going to be, its vertical component has got to be, what did it say, 120? 30 pounds. Yeah, the vertical component. That doesn't mean the total component. The vertical component is 30 pounds. Okay, now, so I kind of hate, they say here the directions are this, but the way they write it, they mean more than direction. The direction would then be some C times that, okay? F sub 2 would be, it's going to be some C also, what's that? √3/2, comma, 1/2, comma, -4. Close that one out. Now, the C's have got to be, well, assuming equal distribution of weight, which appears to be the case here, the C's are going to be the same. So it's not C1, C2, and C3, it's just C, okay? And then let's do F sub 3. And what would that be? C times what? -√3/2. Is that what I heard? (1/2), comma, -4. Okay. Now, because all three legs have the same length, now we didn't verify that, but kind of looking at it, you knew it had to be the case. And the total force is distributed evenly among them. That's why we use the same C for all of them. then the magnitude of all three of these have to be the same. So there does exist some constant, like we just labeled there, that these will be that, and your total force, F, which is, anyone want to tell me what F is? What I called F sub W. Say again? I still can't hear.
Is it the sum of all of them?
It is the sum of them, but simpler. Looking at the figure, what is that? It is the sum of them, and that's what we're going to use. This would be, but what is the value of that vector? 0, 0, that's your weight. 120 down, okay? Okay. Now, so it's some easy way to do this. It's pretty obvious to me that these two have got to add to 0, because it says that's a 0, this would be a root 3 over 2c minus root 3 over 2 and 0, that's going to be 0. That doesn't tell us a lot, okay? Negative 1c plus 1/2 c plus 1/2 c, that's going to be 0, no matter what c is. So all your issue comes down with negative 4c plus negative 4c plus negative 4c has got to be negative 120. Those three added together give you negative 12c, so c must be 10. Okay? So I think that's all you had to do then, is determine what the F1 is equal to 0, negative 10, negative 40. F2 is equal to 5 root 3, 5, negative 40. Ooh, negative 40 or negative 20? Negative 20. Wait. No, negative 40. Okay. Okay. And F3 is negative 5 root 3, 5, negative 40. Okay. Quit that. Okay. So let's see. 0, negative 10, negative 40, 5 root 3, 5, negative 40, negative 5 root 3, 5, negative 40. Done. Whew. That finished 11.2. Okay. Homework exercises here would be either 5 or 7. They're both at Calc Chat. Have 2 parts each. Either 9 or 11. They're both at Calc Chat. 9's at Calc View. Any of the odds 13 to 23, they're all at Calc Chat. 25 or 27, they're both at Calc Chat. 25's at Calc View. 29 or 31, they're both at Calc Chat. 33 or 35, they're both at Calc Chat. 33's at Calc View. Any of the odds 37 to 41, they're all at Calc Chat. 39's at Calc View. 43 or 45, they're both at Calc Chat. 47's at Calc Chat. 49's at Calc Chat. Either 51 or 53, they're both at Calc Chat. 51's at Calc View. 55's at Calc Chat. 57's at Calc Chat. And either 59 or 61's at Calc Chat. 63. Lost it there. Sorry, it was 63. 63 or 65, I think. Yeah. Both at Calc Chat. 63's at Calc View. 67 or 69. Both at Calc Chat. 67's at Calc View. 71's at Calc Chat. 70, any of the odds 73 to 77 are all at Calc Chat. 79 or 81, both at Calc Chat. 79's at Calc View. 83 or 85, they're both at Calc Chat. 87's at Calc Chat, and 89 Calc Chat. Sorry, I can't talk. You can explore doing either 91 or 93. They're both should be at Calc Chat, at least something about them. You can look into doing any of the odds 95, I'd say any of the odds 95 through 103, I think. Yeah, that should do it. All right, good enough. All right, we're about at the place we normally take a break. Do you need one? I can certainly use one myself. My eyes are stealing. It's freezing up on me, it seems like. Okay, so let's pause this. Well, let me go on and clear this screen and go on to we did that. All right. Discard that. And, I should have said this before somebody left. Is anyone leaving? If they're leaving, I've got to get you your test. I hope those who just walked out the door are not leaving for good. So just the two of you? Okay. Now we haven't finished all that, but you can get started on parts of it. Okay. Okay. Have a good weekend. Okay. So we'll move on to 11.3. Actually, I think this is going to work out pretty well. Pretty close. Okay. I'm going to go on and pause the but since it is a decent starting off point again, I'm just going to assume that neither of them probably will be coming in because they've already missed at least half the class. So let me go on and say again, so I won't forget to do it, how we're going to wrap up the term. I know two of you came in after I announced this, right? The rest of you are all here. Okay, so let me just quickly, if possible, go over that. Okay? Today my office hours are from the remaining office hours I have today, 5:30 to 6. Okay? That's sort of standard. Okay? Tomorrow, hopefully I won't have to make a trip to the Birmingham campus until late in the day. So I have office hours from 8 to 8:30, class from 8:30 to 10:45, office hours from 10:45 until 4:15 approximately. Okay? 4:15 I've got to leave to go to the Birmingham East Campus to teach a physics class. Okay? So that's tomorrow. That same thing, the same hours will be on Tuesday. Okay? Now, you may say, well, I'm going to tell you this just in case you have anything you're looking for and trying to turn something in. So let's cover Monday office hours. Just like today's were and will be 8 to 8:30 in the morning, 5:30 to 6 in the evening. That's all I got on Monday and Wednesday. Okay. Monday for this class, Tuesday for tomorrow's classes, those are the last days of class. Final exams are technically due Wednesday and Thursday, okay? Either if you're taking one, you sit in class and take it, or like are giving them to you, then turn them in. However, let me just say this. All right, let me back up one. I think I've said this, but let me say it again. All of your tests and your research papers are due in by Monday, okay? Research papers, I can't return those to you because they periodically ask for samples of student writing, so I have to hang on to those. But your tests, tests 1 and 2, I'm giving those back on Monday. So if you haven't turned those in by Monday, goose eggs, okay? Not good, okay? So please get those turned in by Monday. Now what do I mean by Monday? I will take them today, I will take them tomorrow, or I'll take them Monday. But please get them in by Monday. Because during class on Monday, I'll be returning those to you. Okay. I think that's that. So, let's get to Wednesday. Wednesday, there is no class. There aren't any classes. That's when you come and turn in your finals. Okay? If you choose to. Okay? Now, when my office hours on Monday? 8 in the morning, and unfortunately, only until 12:30 in the afternoon. Because they've called a meeting for the Academic Standards Committee, which I'm on, for 1 o'clock Monday afternoon. That means I've got to leave to go to the Birmingham West Campus. I have to leave by 12:30. Now, what does that mean? That I won't accept her out there? No, I will. If this is the most convenient campus for you and you can't get it to me before 12:30, bring it anytime after 12:30, slide it under my door. My office is room 265, okay? Since y'all weren't here when I pointed that out, here's where it is on the map here. We're right here in this corner classroom here. Go out the door, hang the left, go down that little half flight of stairs there, past the restroom. Almost to the end of the hall, the last office on the left is 265. So if you can't get it to me by 12:30, but you still want to turn it in sometime Wednesday, slide it under my door. Now, if it's more convenient for you to go to the Birmingham campus, you can do that too. You can go to the Birmingham campus and turn it in on Wednesday in room B122. That's the academic building, B122. That's Dr. Carl Pruitt's office. Now, if it's between 1 and 3, I may still be in the meeting, okay? So I won't be there, but Rose Saxon's the secretary probably will be. She'll take it and she'll give it to me when I get out of the meeting. I hope to be back in the office between 3 and 6. So if you come between 3 and 6, you'll probably catch me in B122. Okay? That's Wednesday. Thursday, if you can't get it into me on Wednesday, that's okay. Get it to me sometime Thursday. But here are the times you need to get it to me by Thursday. On this campus, I'll be here from 8 in the morning until about 4 o'clock in the afternoon. Okay? Because I've got to go to the Birmingham East Campus to pick up finals there. Okay? Well, with that in mind, please get it to me here by 4 o'clock. And that way I can take it over there and grade it. Now, if you don't get it to me by then, you'll need to catch me on the Birmingham East Campus. Now, that's right across the road from the Birmingham West Campus, and it's in the Ethel Hall Nursing Building in room 214. That's where I'll be up on the second floor. I'll be there from 5 to 6:30, probably after 6:30, but not long after 6:30, 5 to 6:30 approximately. I may be there a little before 5 and a little after 6:30, but that's it. If you don't get it to me by then, either here before 4 o'clock, there before 6:30, I'm probably not going to get your final until I get back, because I'm going to be putting in for a day off Monday, so we'll be leaving town. I'll be going home from here, and we'll be leaving town first thing Friday morning. So I have to have it, otherwise you'll get an incomplete, and then once I get back, if it's under my door or wherever, then I'll grade it. Now, if you miss that deadline, don't be taking it to Rose Saxon's office or B1-214 after I'm already gone, because I'll never see it then. If you're going to turn it in late, turn it in 265 here. I'll come in that office. So, does that make sense? All right. And the other thing, please do the student course evaluations if you haven't already. The deadline for those is August 8th. I won't be here to remind you on August 8th. I promise that. So please get them done as soon as you can. All right. Any questions? I think I covered those bases there. All right. We're still in Chapter 11, Vectors and the Geometry of Space. 11.3 is the dot product of two vectors. Okay. Are any of you familiar with dot products? Yay or nay? Somewhat? Okay. Our objectives here are to use properties of the dot product of two vectors. We haven't even defined what they are or what the properties are, but we'll be using those. We'll be able to find the angle between two vectors using the dot product. By the way, there's at least two different definitions for dot product. We'll use them interchangeably. One of those involves the angle. We'll find the direction cosines of a vector in space. That's using dot product as well. We'll find the projection of one vector onto another vector using some of those direction cosines. And we'll use vectors to find the work done by a constant force. So, what in the world is a dot product? If you flash back in your minds, and you remember when we talked about some of the characteristics of vectors, the equality of vectors, we talked about that. Each component individually has to be identical with the other for two vectors to be equal. We also talked about adding two vectors. It didn't matter what order you added them, the order is insignificant. You know, they're commutative. Subtraction of the two vectors, we gave definitions for that. Then when it came to multiplication, we only did what we call a scalar multiple of a vector. In other words, a scalar number times a vector. It just scaled up each component. We didn't talk about multiplying two vectors. That's half of what the dot product is. It's one form of multiplying two vectors. The next section, we'll talk about the cross product. Now, if you remember in math, probably when you're way young, you use a time sign, okay? But then later when you got into algebra and you used x for your variable a lot, you started not using a time sign, and sometimes we just write parentheses next to each other or put that center dot. When it gets to vectors, you got to use them both. One type of multiplication of two vectors is called the dot product, which is the dot, okay? The second kind is called the cross product. Two completely different operations. So there's two different ways to multiply two vectors together. Scalar times a vector, yeah, it's pretty simple. To multiply two vectors, we're going to talk first about the dot product. Next section, the cross product. You'll study two operations of vectors, vector addition and multiplication by a scalar, what I was just saying, each of which yields another vector. In this section, we'll study a third vector operation, the dot product. The surprising part here, it does not yield a vector, it yields a scalar. Later, when we do cross product, it goes back to yielding a vector. But the dot product yields a scalar, not a vector. So here's one definition of a dot product. Like I said, we're going to have another one coming up later. The dot product of vector u, which is component, now here's two-dimensional, there's three-dimensional, so both of them are here. U, which is u1, u2, and v, which is v1, v2. By the way, we don't multiply a two-dimensional vector by a three-dimensional vector. We don't do it. They've got to be the same dimension, okay? So the dot product of vector u, u1, u2, and vector v, v1, v2 is this. U dot v is simply the product of their first components, u1, v1, plus the product of the second components, u2, v2. And notice, that's now a scalar. That's a scalar, plus a scalar is a scalar. Okay. Dot product, if you have three dimensions or higher. Now, we're not going to go into higher dimensions, but if you had higher dimensions, like in linear algebra or somewhere, still true, the dot product of u, which is u1, u2, and u3 in three dimensions, v and v1, v2, and v3 in three dimensions, is u dot v would be u1, v1, plus u2, v2, plus u3, v3. Just multiply the corresponding components together and add those up. That's your dot product, or at least one definition of a dot product. Okay? It's an easy one to do. Now, sure the later slides are going to say this too. Notice what happens if you reverse the order. If you do v dot u, that would be v1u1 plus v2u2. Guess what? Multiplication is commutative, addition is commutative, it doesn't matter. You get exactly the same result. Okay? Same thing down there. So dot products, it doesn't matter which order you do, they're commutative. Okay? Everybody got it? So here are some properties of the dot product, some of which I've just said. In this case, we've got u, v, and w are all three vectors in the plane or in space, whichever, but they've got to be in the same dimensions, okay? C is any old scalar, any real number scalar. And this is what I just said, u dot v is exactly equal to v dot u. Absolutely, no problem with that at all. Now, that's a commutative property of dot products, okay? Now, number two is a distributive property of a sort. U dotted across the sum of two vectors v and w would be u dot v plus u dot w, okay? U plus v is a vector. Dot that with another vector, you get a scalar. This would be a scalar plus a scalar is a scalar. That doesn't prove it, but at least it shows it's consistent. This time, however, we're going to distribute, or not distribute, it's sort of like associate, okay? It's called the associative property of a scalar with a dot product. Well, a dot product of two vectors is a scalar, and a scalar times a scalar is a scalar. So let's say if we get scalars here, we can do it. That would be the same as distribute or associate the c with the u, and then dot that with v, or associate the c with the v and dot that with the u. In any order, those three are all equivalent expressions. Exactly. Now, this one hopefully would make sense. If you dotted the zero vector, which remember has components either 0, 0 if you're in the plane or 0, 0, 0 if you're in space, dot that with vector v, which is v1, v2, or v1, v2, v3, and 0 times v1 is 0, 0 times v2 is 0, 0 times v3 is 0. That multiply, the dot product is the scalar number 0. This is the vector 0, that's the scalar 0. Now here's one that does come in pretty handy. When you dot a vector with itself, you get magnitude squared. And of course that sort of makes sense too, because if both of these were v's, say, then this would be v1, v1, that's v1 squared plus v2 squared plus v3 squared, and that would be the square of the square root of those very things. So that is your magnitude squared. So actually we get another way to do a magnitude of a vector, dot them and take a square root. It's exactly the same operation. Okay. Any questions on those? Everybody got it? All right, let's do an example here. Here we have u is negative, or 2, negative 2, v is 5, 8, and w is negative 3, negative 4, 3, if I can read. What is u dot v? You tell me.
It's going to be
10
plus 16
is it plus?
minus
Minus 16 would be negative 6, okay? It would be u dot v, which is 10 minus 16, which is negative 6. Okay? Good deal. Let's next do u dot v times w. What's u dot v? We just got it, right? Minus 6 times w. You got it? 24, comma, negative 18. You got it. Now here we had a scalar times a vector produces a vector. and sure enough it does. 24, negative 18. Make sense? Okay. Let's do the C. All right. What is U dotted with 2V? Or not 2V? Okay. What would that be? There's at least 3 different ways you could do this. How do you want to do it?
Just go ahead and multiply 2.
Okay, and we've already done that. Oh, wait, 2 times V? You could do that. I'm lazier than that. One other way to do this is either 2 times U dot V or 2 times U dot V, but we've already done U dot V. So what would that be then? Negative 12. Be lazy. No, work hard. Whatever. Okay. And this would be 2 times negative 6, which we've already done, and that is negative 12. Make sense? All right. Let's see if there's a D part. Yes, there is. What in the world is the magnitude of W squared? What would you do to get that? Second?
So the magnitude of U dot V squared?
Yeah. Magnitude of W squared.
W.
Just W dot W. And that would be? 16 plus 9? 25. Okay. So the magnitude would be square root of 25, which would be 5. But the magnitude squared, just the dot product of the two. Pretty easy to do. Okay? I don't think there's an E. Let's see. No. Notice that the result of part B is a vector quantity. We already said that. Whereas the results of the other 3 parts, dot, 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 those are all scalars. This is dot times a vector. Scalar times a vector is a vector. Okay. That was example whatever. 1. All right. Now, here comes another definition of a dot product. This one enables you to find an angle between 2 vectors. Angle between 2 non-zero vectors, because remember, a 0 vector has no direction, no magnitude, so it can't have an angle. Okay, so the angle between 2 non-zero vectors is the angle theta, and we always define that to be less than pi, between 0 and pi. So it can be an acute or an obtuse angle, but nothing beyond that. Okay, between their respective standard position vectors. Okay, here's a figure of it. The next theorem shows how to find that angle using a dot product. So if this is your vector U, there's your vector V. The angle between the 2 vectors is that. Now here they show V minus U, which was totally unnecessary to do, but it's correct. I mean, if you did this is vector U and added V minus U, the plus V minus U goes away and that gives you V. So that's fine, but we're just going to see if we can find that angle. It really has nothing to do much with the difference, but you could write it that way. All right, so here's theorem 11.5, angle between 2 vectors. Basically is another definition of a dot product. If theta is the angle between 2 non-zero vectors, U and V, where theta is between 0 and 90, 0 and 180, or 0 and pi, okay, then the cosine theta is U dot V divided by the magnitude of U times the magnitude of V. Now I said this is another definition of dot product. It is. If you just multiply these by this, there you have. The dot product of U and V is the magnitude of U times the magnitude of V times the cosine of the angle in between. Now it's been a long time, but my vague memory way back there was saying to me, this is the first definition of dot product I learned rather than the product of their components added together. We used them both, but it seems like we learned this one first. Okay? Now, notice a couple things here. Magnitude of U is always positive. Magnitude of V is always positive. They're magnitudes, lengths. They're going to be positive quantities. Square root, positive square root of sums of squares. Okay? Always positive. U dot V could be negative. Okay? If it's negative, that means your angle theta is obtuse, between 90 and 180. If it's positive, it's between 0 and 90. Okay? So cosine will always have the same sign as the dot product. So what I was just saying, the dot product is negative, theta is between pi halves and pi. If the dot product is positive, it's between 0 and pi halves, because that's how we define the angle. All right. Now, here's the possible orientations of the two vectors. If they're exactly in the opposite direction, what is the angle here?
180.
180 or pi. And what's the cosine of pi, or 180? Negative 1, so the cosine is negative 1. That would give you that situation, theta equal pi, cosine negative 1. If you're second quadrant with that angle, in other words, it's an obtuse angle between pi halves and pi, then the dot product is always going to be negative. Okay, so you're between those two, so your angle is between the value of the dot product between negative 1 and 0. Always negative. If U and V are perpendicular, guess what? The angle there would be pi halves, or 90 degrees. And what's the cosine of 90? 0. This is the key. Okay? If you have two vectors, the dot product, which is easy to calculate, is 0, they've got to be perpendicular. Got to be perpendicular, no way around it. Okay? If it's -1, they're opposite directions. Negative, obtuse, positive, acute. Okay? U dot V would be magnitude of U, magnitude of V, times cosine of that angle, cosine in the first quadrant, always positive, so this will always be positive. Okay? If, however, they're in the same direction, U and V are in the same direction, your theta there is 0, cosine of 0 is 1. So if you have a dot product of two vectors being back off from that. Exactly, okay. The magnitude of one times the magnitude of the other, that means they're collinear. Okay? And in the same direction. Collinear in opposite direction, the dot product is -1. Cosine is -1. Okay. Now, from that previous theorem, you can see that two non-zero vectors, this is what I was saying, meeting at a right angle, if and only if their dot product is 0. Such two vectors are said to be perpendicular, they're said to be at right angles, or the other name for it, orthogonal. Later we'll also add the other name, normal to each other, meaning perpendicular to each other, orthogonal to each other. Okay? So the definition of orthogonal vectors, two vectors U and V are orthogonal if and only if their dot product is 0. Okay. So here's example 2. Page 772. If U is 3, -1, 2, V is -4, 0, 2, W is 1, -1, -2, Z is 2, 0, -1. Okay, all those memorized? Okay. Now, find the angle between each pair of vectors, U and V. What would be the angle between U and V? Let me get my pen set up. Okay. I'm going to say theta UV. The angle between U and V. What would that be?
Inverse cosine.
Okay, the inverse cosine of,
U dot
second,
U dot
can't hear, U dot V. Is that all?
over the product.
Yeah, over magnitude of U times the magnitude of V. Okay, because cosine theta is that, the theta would be the inverse cosine of that. So let's see if we can calculate those fairly quickly. Inverse cosine of U dot V.
Negative 12
-12.
plus 0.
Yeah.
Right?
Right. Plus 4, is that what you said?
Yeah.
Okay. Divided by
Square root of 1.
9 plus 1 plus, not that hard, is it? Square each of the terms. 9 plus 1 plus 4, right? Times the square root of 16 plus 4. Okay? Let me. It's just a silly place to put that. Whoa! That's not what I wanted. Okay. Alright. And that's equal to numerator inverse cosine of -8 over
Square root of 15 times the square root of 1.
okay. And I think I'll have to divert to letting you do your calculator. Okay. You can pull a root 2 out of this and a root 2 out of that, and that would give you a 2 here. Let's see if that would help any. Inverse cosine of -4 over root 7 times root 10, which would be inverse cosine of -4 over root 70. Let's see what that gives you.
Isn't it root 15 plus root 20?
I'm sorry,
times root 20 though?
I can't hear.
Isn't it root 15 times root 20?
Okay, I can't hear.
On the bottom?
Right.
Isn't it root 15 times root 20? Or is it
Is that 14 or 15? This is 14, isn't it? Did I do it wrong?
plus 1 plus 4?
9 plus 1 is 10, plus 4 is 14.
Oh, I'm sorry.
Is that right?
Yeah.
Okay. Good. Ray, the old gray cells
Oh,
were
okay.
leaving town on me. Okay. I hope I did that right.
Yeah.
Pull a root 2 out of each, and root 2 times root 2 is 2. That would go into that. So I think that gives you that. See what you get, and let's see what they got. Yeah, I think we're getting the same thing. What kind of angle do you expect to see? Obtuse, okay, because it's negative. Now what's
118.6.
second?
118.6.
Okay, that's in degrees. Most of the time they're going to give these in radians, and I can't look at it easily and say, oh, that's obtuse, but you can sort of. They gave about 2.069 radians. Which would be approximately, what you say, 118 degrees. That is a lot easier for me to see. Now, you can do it with radians, but here's what you have to do. Remember that pi halves would be approximately 1.5 27, is that right? 3.1614. Yeah. Something like that. And this would be greater than that, but less than pi. So, so yeah, this has to be second part too. Just a little harder to think of. Okay, there's the A part. Let's do the B part. Want to do that in a different color or erase A? I don't care.
Green.
Second? Green, okay. Green, green, it's green, they say, on the far side of the hill. You wouldn't remember that. Okay, so what would be the angle between U and V, U and W? Theta sub UW would be, still starts off with inverse cosine. Now what would that be? Get out of there. Okay, it did say U and W, right? Okay, what does that give you? 3. Okay, that's 4. Which is?
0.
Ding, ding, ding. What can we tell? Theta is equal to? Pi halves. Okay, perpendicular, orthogonal. You don't need to mess with the denominators. Who cares? If that numerator is 0, the whole argument is going to be 0. Okay, so that one was a really nice one. Okay, the C over here, what color you want that one? Any? Red. Okay, we'll see if red will come up. So let's do the theta between V and Z. That's the inverse cosine of
-8.
okay, V and Z. Yeah, there we go. -8. Second.
-8 plus -2.
Right, so that would be -10. What kind of angle is this? Obtuse, sure seems like it. Except for this, let's just pause a moment here. Not quite. Because V and Z, right, they're exactly opposite directions, aren't they? Because -4 is exactly -2 times 2. 0 is -2 times 0, and 2 is -2 times 1. So yeah, not going to be 0, they're going to be that'll be 180. Okay, so this will be, we can go on and just say that. This is equal to either 180 degrees or pi radians. Okay. Don't want to waste too much time doing that. But let's, you could go through the other mess with it. Nothing would pop out. You see it there. Okay. Oh, yes, it would. Okay. That gives you -10. And then let's see what happens if you do the magnitudes. Okay. Magnitude of V would be what? Magnitude of V?
16 plus 4.
16 plus 4 is?
12. 20.
Square root of 20. And Z? Okay. And square root of 20 times square root of 5 is? Hike. Okay. Okay, square root of 100, which is 10. You get negative 10 over 10. This would be the inverse cosine of minus 1. Okay, and that, of course, is pi or 180 degrees. All right, good deal. Now, let's see how they do it. Hopefully, nicely. Can I erase? Okay. All right. So for the first one, the cosine of the angle theta will be the dot product between u and v, which we did to be found to be minus 12 plus 4 is minus 8 divided by root 14 times root 20, and that would be minus 8 times 2, and they pulled the minus 4 out of root 20. I pulled root 2 out of each one. It doesn't really matter. And that would be minus 4 over root 70, and because that's less than 0, you know your angle theta is an obtuse angle, and the inverse cosine of that would be, they use arc cosine, I prefer inverse cosine, negative 4 root 70, which would be about 2.069 radians, which we found to be about 180 degrees. All right, the B part, when you did u dot w, you got 3 plus 1 minus 4. That adds a 0. Who cares what the denominator is? That's going to be a 0. They care. That's root 84. But that's just going to be 0. The inverse cosine of 0 is pi halves. Okay? So u and w are orthogonal, perpendicular, right angles to each other, however you want to call it. So that angle is pi halves. Now the C part, v dot c, would be negative 8 minus 2 is negative 10 over root 20 times root 5, which sounds familiar. That would be root 100. Negative 10 over the square root of 100 would be negative 10 over 10, which is minus 1, which would be your angle theta must be pi. B and Z are parallel but in opposite directions. The U and W were in the same direction. Okay, your dot product was 0. Okay. When the angle between, we're perpendicular to each other because the angle is 0. When the angle between two vectors is known, rewriting the theorem 11.5, and this is what I was talking about, you've got u dot v, dot product of two vectors, is magnitude of u times magnitude of v times the cosine of the angle between them. If you knew that angle, then you can get the dot product this way. Much easier to just multiply components. Produce an alternative way to calculate the dot product, but more importantly than that, if you know the dot product another way, and the magnitudes of the vectors, you can come up with the angle pretty easily. Okay. Now, let's see. There was example 2. And they're skipping example 3. So let's go back and do example 3. All right, we'll do it here. Oops. How? Oh, yeah, we went to red. I was thinking, how does it go back to red? Okay, example 3. What if you know that the magnitude of vector u is 10? Okay? And you know that the magnitude of vector v is 7. And you happen to know that the angle between u and v is pi fourths. So theta between u and v is pi fourths. Find u dot v. Most of the time you're not going to know this, but if you did, what would that be?
7 times n times
That would be 10 times 7 times cosine of pi fourths. And what is the cosine of pi fourths? Square root of 2 over 2. 2 will go into 70, 35. So that would be 35 root 2. There's your dot product. Okay, 35 root 2. That was nice, wasn't it? Okay. All right. Now let's move toward direction cosines. Sort of seems like a strange combination of words, doesn't it? In space, it is convenient to measure direction in terms of the angles between the non-zero vector v and the three unit vectors I, j, and k, as shown here. So if this is your vector v, now we can't see where that v is. It looks like it could be in the plane or it could be somewhere else. But how you would reference that is the angle between v and the I unit vector. That would be your alpha. Angle between, and here's where that projects down to. So we see you're in the first octave. Just a little ways out on x, quite a bit further on y, and not too far up on j. Okay? K or z. Okay. Now, so the angle alpha is the angle between I and the vector v. Angle beta is the one coming up for y or j to the vector v, and the angle gamma is from k to the vector v. Okay? Those are called your direction angles. Okay? Measure direction in terms of the angles between the non-zero vector v and the three unit vectors. Okay? Not a very easy thing to measure, but maybe not so bad to calculate. Let's see. The angles alpha, beta, and gamma are direction angles of v, and the cosine alpha, cosine beta, and cosine gamma are called the direction cosines of v. Now, what would be the quantity v dot I then? Well, that would be, from our last definition, magnitude of v times magnitude of I. Anyone tell me what the magnitude of I is?
square root of -1.
Yeah. 1. Okay, square root of 1 is 1. So unit vectors, magnitude is always 1, times the cosine of alpha. Okay? Well, since magnitude of I is always 1, this will just be magnitude of v times cosine alpha. So even though alpha may not be an easy thing to measure, calculating it isn't bad at all, because v dot I is just going to be the v sub 1, right? V sub 1, that's it, divided by magnitude of v. There's your cosine alpha right there. Because v dot I is v1, v2, v3 dot 1, 0, 0, v1 plus 0 plus 0. That's just v1. So it follows that cosine alpha, while it's not an easy thing to measure, it's a really easy thing to calculate. It's the component of your the vector in the I direction, because this is the alpha angle times the magnitude, divided by the magnitude. Okay? That's it. I mean, that's all there is to it. Okay? V sub 1 divided by magnitude of v. Okay? By similar reasoning, the unit vectors j and k, you have cosine alpha is v1 over magnitude of v, cosine beta is v2 over magnitude of v, and then cosine of gamma is v3 over magnitude of v. So guess what? You calculate that once and then divide. That's all you got. Okay. Again, easy angles to calculate, not so easy to measure, but easy to calculate. Okay? Consequently, any non-zero vector v in space has the normalized form. What do we mean by normalized? We mean by that the unit vector is normal, 1. Its magnitude is 1. Okay? And that would be v sub 1 over magnitude of vi, v sub 2 over magnitude of vj, magnitude of v3 over magnitude of vk, which is just the cosine alpha I plus cosine beta j plus cosine gamma k. Again, not easy things to measure, but certainly easy things to calculate. Okay? And because that's a unit vector, it follows that cosine alpha squared plus cosine beta squared plus cosine gamma squared have to be 1. Because this thing is a unit vector, so its magnitude is 1. That is its magnitude. I mean, this is the vector, and so the magnitude of that vector has to be 1. Okay? Now, example 4. Find the direction cosines and the angles for the vector v is 2i plus 3j plus 4k. Okay? So, oh my goodness gracious. Let's first do the direction cosines. What is cosine of alpha? Okay. This would be 2 over second 4. That would be the square root of 4 plus 9. Okay.
The square root of 25, 5. Right?
Okay. The square root of 4 plus 9 plus 16. Right? Okay. Which would be 2 over the square root of 29. Is that what you're saying?
Yeah.
Okay. My hearing is so bad I couldn't make it out. Okay? That is your direction cosine. You don't need to find the angle. They just said, oh, no, and the angle. So let's do the angle. What would alpha be then? The inverse cosine of 2 over root 29. I can't do that in my head. Don't need a calculator. Fairly small angle, I would think.
68.2.
Second?
68.2.
Degrees. Okay. 68.2. Oh, yeah. I'm sorry. Not a very small angle. I was thinking sine. Cosine would be a pretty good size angle. What would that be in radians? That's a little over 1. What, 1.2 or 3? Oh, never mind. They give it in degrees. Sorry. I thought for sure they'd be doing it in radians, but it's fine. All right. So let's do the next one. Cosine of beta is 3 over root 29. You don't have to go back and recalculate that. It's just 3 over root 29. So what would beta be? A little louder. Inverse cosine of okay. Why did I put the square root up top? I don't know. 3 over root 29. Okay. And what would that be? 56.1 degrees. Okay, good for them. And cosine gamma. That's a pretty ugly gamma, isn't it? Okay. That would be 4 over root 29, and that would produce gamma approximately equal to 46? 42. Okay, I'm sorry. 42.0 degrees. Okay? I left off the inverse cosine part, but there we have. Now, let's just take, this is real easy to show that last part, because when you square this, you get 4 plus 9, 13 plus 16 is 29 square root of 29 over square root of 29, I guess is 1. Okay. So, or 29 over 29 is 1. Okay. So, wasn't hard to show. All right. Any questions on direction cosines? Nice little concept, really not one we wind up using that frequently, though you can, and it does have some good characteristics. So what I'm going to do is let's pause here, clear here, and let you see how they did it. Okay. Now, they were sort of looking ahead pretty much and said, yeah, first thing you got to do, or you're going to have to do for every part of the problem, is know what the magnitude of V is, so go on and do it. And that gave root 29. Okay? Leaving Athens, Georgia. No. Okay. And the cosine of alpha would then be the x component over that, 2 over root 29. Making the angle about 68.2 degrees. The cosine beta is V2 over that, 3 over root 29. And that would be about 56.1 degrees, and gamma would be 4 over root 29, which is approximately 42 degrees. Okay. Furthermore, the sum of the squares of those would be 2 squared is 4 over 29, 3 squared is 9 over 29, 4 squared is 16 over 29, add those together you get 29 over 29, which is 1, which is pretty easy proof. Okay. All right. There was they've taken it and twisted it a little bit. Same type of deal here. Oh no, this is a different problem. This is 2x, 3y, and 4. 2i, 3j, and 4k. Now, I have to always sort of make a guess on this. If that's your 4 there, yeah, that looks about right. Okay. Sometimes it just looks like those don't quite line up because you've got the x-y plane falling down ahead of you, and so this gets projected down quite a bit. Okay. All right, we're now ready for projections and vector components. Okay. You've already seen applications in which 2 vectors are added to produce a resultant vector. We did that by component notation was the easy way to do it. You could do it by parallelogram method. You could do it by geometric, however you're going to do it. Many applications of physics and engineering pose the reverse problem, decomposing a vector into the sum of 2 vector components. Happens all the time. The following physical example enables you to see the usefulness of this procedure. Okay? And here you have it. Okay? Now, this is not a numbered example. It's just an example. When I first read that, I said the following physical example is not a numbered example. Consider a boat on an inclined ramp here. Now, they don't tell you much about that ramp. Seems like they would tell you the angle of the ramp. They don't. Consider a boat on an inclined ramp as shown in figure 1128. The force F due to gravity pulls the boat down the ramp and against the ramp. And I'll tell you what that means in just a minute. The two forces W1 and W2 are orthogonal, and they're called the vector components of F. Okay. Now, frankly, the Earth is pulling down on this boat and trailer, whatever it's on, straight down. That is a force due to weight. So I like to do it capital or bold F or F, vector F, and I usually do a sub W, meaning the force due to the weight of that. Okay? Now, that force straight down has a component parallel to the ramp and perpendicular to the ramp. The one perpendicular is the one they meant when they said against the ramp. Okay? Pulling down perpendicular to the ramp. Have any of you taken physics yet or taking it now? I know you are. Okay. Okay. That is sometimes called the normal force. That's normal to or perpendicular to the surface. The W1 is the force pulling you down the ramp. Okay? That's the thing that's you're having to do with your boat, with your truck or whatever you're pulling that with. You're having to exert a force equal to that to keep it from rolling down the ramp. The perpendicular component is just the force of the wheels on the ramp or the ramp on the wheels, whichever you want to do it. Okay. So I really don't care for W1 and W2. I like to call this, if you call this one W, then I call this W parallel and W perpendicular. That to me is easier and more direct than 1 and 2. Perpendicular sign is the one like this, and the parallel sign is like that. That's how I like to set up the problem. So I don't have to remember. Now, which one is 1 and which is 2? Is that parallel or is that perpendicular? If I have perpendicular parallel there, I see it. Okay, so your total force, or the weight, is the sum of those two, the vector components of your force. The forces W1 and W2 help you analyze the effect of gravity on the boat. For example, W1, that's down the ramp, I'm pretty sure, indicates the force necessary to keep the boat from rolling down the ramp, whereas W2 indicates the force that the tires must withstand to push against the ramp. All right. Man, my voice is going on me. All right. So, if U and V are non-zero vectors, good, and that U is W1 plus W2, the weight parallel to the ramp times the weight plus the weight perpendicular to the ramp, where W is parallel to V and W is orthogonal to V. Okay? So now we're not talking about ramps anymore. Okay? This is W1 is parallel to some other vector V, and W2 is perpendicular or orthogonal to V. These are the two components that add up to the vector U. Okay? As shown here in these figures. Okay? So here's your vector U going up here. Vector V is in standard position in the positive horizontal direction. Okay? So W1 is the component parallel to V. It happens to be a good bit longer than V. That's okay. It doesn't matter. And W2 is the component perpendicular to V. And that's pretty important here too. Okay? U is the sum of those. And W1 is called the projection of U onto V. Okay? And in this case, the V is shorter, so your projection is extended past the length of V. There it is, the projection of U onto V, or the vector component of U along V. And that's denoted by W1 is equal to the projection in the direction of V of the vector U. U is the one we started with, the projection in the direction of V of this vector U. So this may not be a beneficial way to look at it, but here's how I think of it. Imagine you had a very bright light close to infinite distance above this, and you're shining that onto vector U, with vector V being perpendicular to the light, normal to the light, okay, right there. The shadow that you would cast here in the direction of V, that's the projection of U onto V. That would be the shadow of U in the direction of V. I don't know if that's helpful, but that's how I like to think about it. And that's for projection would be a shadow. I mean, you get the idea. Okay. W2 then is the component of V that is a component of U that is perpendicular to vector V. Well, an easy way to say that is just W2 is U minus W1, okay? Because W1 plus W2 is going to be U. These are the two components, the parallel component and the perpendicular component to vector V. So that's an orthogonal system, and it works. In this case, your angle theta is an acute angle. It could be that with vector V in this direction, with vector U in this direction, its projection onto the x-axis, you might say, the axis where V is located, since it's a standard position, is back over on this side. So therefore, this will be an obtuse angle. Okay? Theta is obtuse here because the projection is in the opposite direction of your reference vector V. Okay? W1 is the projection of U onto V, and vector component of U along V. And W2 is the vector component of U perpendicular to V, which is also U minus W1. Okay. Here's example 5. I think we have time to do it. Let's see if we can. Find the vector component of U, which is 510, that is orthogonal to V, which is 4,3. Given that the W1, the projection of V onto U, is 8,6. Okay? Now, that looks reasonable because it is a multiple of 4,3. It happens to be exactly twice 4,3. So you know those are in the same direction. And U has to be the sum of W1 and W2, but you know this is W1. So it's not too hard to figure out what W2 is. Find the vector component of U that is orthogonal to V. So the one, this is parallel to V. The one orthogonal to V would be W2. That is a vector, is equal to what? Here we have it. W2 is U minus W1. So that would be 8,6 minus, I'm sorry, it's U first, 510. I was going to say, where did it go? There it went. Okay. U is 510 minus 8,6 And that would be
-3.
-3, 4. Okay. Pretty ugly angle brackets, but there they are. Okay. I'm not absolutely certain they want us to do it that simply, but it certainly can be done that simply. Okay, so let me clear mine out of the way. All right, because U is equal to W1 plus W2, where W1 is parallel to V, it follows that W2 is the vector component of U orthogonal to V. So we have W2 is equal to U minus W1, which is exactly what we did, and that would be 510 minus 86, which is -3,4, precisely. All right. I guess that's shown everything we need to. Check to see that W2 is orthogonal to V, is shown here. How could you check that real quickly? W2 is orthogonal to W1. Here's W1, W2. That's what you file your income tax with. What's that? How can you check to see if those are indeed orthogonal? Dot product. What's the dot product?
-24.
-24
24.
is 0. And for two vectors to be perpendicular, orthogonal, the dot product is 0. And sure enough, that is the case. We did the math, and it sure seemed right. Easy check to see that. Now, is drawing pictures good enough? No. Okay, I can't ever tell if I've got an exact right angle or not. Some can look awfully close to right angles and not be right angles, but dot products don't lie. Okay, okay. W1, 86, W2, -3,4. Do the dot product -24 plus 24 is 0. Okay. That's the easy check. All right. Any questions on that? Okay. I think we're just about out of time, aren't we? Okay. So we'll pick up next time with Theorem 11.6. Okay? Top of page 775. Let's see if we got enough done to have any homework exercises. Oh, we're saying things pretty close to finishing. Think you can do any of the odds 3 through 9. They're all at Calc Chat. 3's at Calc View. Any of the odds 11 through 17, they're all at Calc Chat. 13's at Calc View. Do 19, it's at Calc Chat. Any of the odds 21 to 25, they're all at Calc Chat. Wait, 19 was both at Calc Chat and Calc View. I didn't say that right. Okay, either 27 or 30 or 29, they're both at Calc Chat. 31 to 35, they're all at Calc Chat. 31's at Calc View. And any of the odds 37 to 43, they're all at Calc Chat. 37's at Calc View. Okay, I think we'll hang off the rest of those until next time. Okay? All right, we'll begin there. Any questions? All right, just to look ahead, we're going to finish 11.3 next time, move on to 11.4. This will be Monday. Okay? And I think we'll have time to at least get started in 11.5. We may not finish it, but we hopefully will get progressed into 11.5. That's where we stop. 11.6 is the beginning of Cal 3. Okay? Strange the way they do that, at least here. I don't know what it is at your school, but that's what it is here. All right. Good deal. Any questions? All right. Have a good weekend.